Good morning, everybody. Welcome to the last day of MECO45. And we are going to start with the morning session in a few minutes. This morning session will be about a very interesting field on the borderline of life sciences and chemistry and physics, a truly interdisciplinary subject. And we have outstanding speakers today. So I'm really looking forward to this program. I think we should really wait one more minute just to the speakers in order to have some time for discussions. I'm going to give a sign, a sound sign somehow, maybe like this, 5 minutes before the end of the talk. Okay, so the first talk will be an invited talk by Julyan Cartwright, and the title is Chemobrionics and the Origin of Life. Julyan, please.
Thank you. Do you see now my screen?
Yes.
Good, very good. So thank you for the invitation. Let's get started. So at the moment in 2020, there are two main theories for how life may have begun on Earth. One is what's shown on the left, and the other is what's shown on the right, basically. So either life began on the surface of the planet in some pond, some water on the surface, or it began at the bottoms of the oceans in hydrothermal vents at the bottoms of Earth's oceans. I'm mostly going to concentrate on the theory on the right, the hydrothermal vent theory, though I shall make reference to both at points along the talk. In any case, the main question is this, that life needs water, at least life as we know it needs water to begin. And we know that there was water on the early Earth. We just are interested in working out the most likely place where life began in this 4 billion years ago on the early Earth. And from the 1990s onwards, there's been an amount of work by geologists and geochemists and then chemists and eventually physicists like myself and others in trying to understand the origin of life on Earth. And that is in part what I'm talking about this morning. So these hydrothermal vents were discovered on Earth in the 1970s. They occur at the bottoms of the oceans. Those are two submarines that you see illuminating the vent. They are structures that are tens of meters tall at the bottoms of the oceans. They occur where hot fluid is coming out of the Earth and depositing minerals, which arrives at these extraordinary shapes that you see here and gets to be tens of meters tall, and these vents last hundreds of thousands of years. So they're very long-lived, very large, important structures on the ocean floors. If you are interested in this topic, I recommend, by the way, this review paper, The Inevitable Journey to Being. So I just thought I'd put that slide in. So I'm going to talk quite a lot in this talk about chemical gardens. Some of you may have done some school chemistry and have seen these things in a school chemistry lesson, or perhaps seen them for sale in the science section of children's toy shops. They are very interesting, a very interesting chemical reaction that is much more than a toy, however, and they are what is producing the hydrothermal vents at the bottoms of the oceans. So this is a video from a Chinese group showing the growth of these systems, and it just gives an idea of the complexity of the processes that are going on during the growth of these systems. You see formation of vesicles, formation of tubes. You see that it's a combination of precipitation chemistry and a lot of fluid mechanics. You can see much fluid movement. So to understand these structures, one needs both the chemistry and the fluid mechanics coming together, which makes it very interdisciplinary. So what one is basically talking about in the formation of these structures is a self-organized formation of a semi-permeable membrane. That word or phrase semi-permeable membrane immediately strikes some resonance with biology, because biology is full of such membranes. And in fact, the whole importance of what I'm talking about this morning is the fact that this type of self-organized chemico-physical system is able to produce these membranes, and these may have been involved in the origin of life. So the formation mechanism that's known for these chemical garden systems is the following. You see on the left, the classical experiment, you put a metal salt crystal into a solution, which is often of sodium silicate, and then a chemical reaction occurs. And in the chemical reaction, the acidic solution of the metal salt crystal, when it dissolves, reacts with the alkaline solution of the silicate and produces a solid, a precipitate, which is a silicate hydrate solid. That's the chemistry. But the important point from the physics is that the physical properties of this membrane are such that it's semi-permeable. It allows some molecules through and others not. What that means is that there's still communication between the two sides of the system after the formation of the membrane has begun. And because of that, the reaction continues. And so osmotic pressure builds up inside the membrane, and eventually it breaks. And when it breaks, usually in the classical experiment, buoyancy forces mean that the fluid flowing out flows upwards, and you get tube formation around a jet of fluid flowing out. So that's the basic mechanism of the formation of these tubes, which is already a complex system. And I should say that this is just a summary of the chemistry involved, the different possible chemistries. There are huge numbers of precipitating anions and cations that can be involved in these reactions. What that means is that the chemistry is not specific to a given chemical system. It's really more a question of materials physics or materials science in having a semi-permeable, a porous membrane through which things are flowing. And so this means that we now get into this sort of physics, so the physics of porous membranes, which takes you through to interesting part of fluid mechanics. And one can study, in fact, people are studying this sort of fluid mechanical systems. From the point of view of my talk today, the question is, were these chemical garden systems, reactors, the first proto-cells? So how does this work? This is a summary picture of how the situation might have been on the early Earth. So at the top left, it says we're looking at the Earth about 4.3 billion years ago. The Earth then had a rather different ocean chemistry than it does today, and atmospheric chemistry. So there was no oxygen, there was an atmosphere of 1 to 10 bar, plenty of CO2, etc. We think that already the tectonics on Earth, the solid fluid mechanics of the Earth at that point was already producing tectonic movements, and so that there was already systems of seawater flowing into the crust and getting heated and coming back out as hydrothermal vents. We believe that that was the case at this period also. And so the idea is that the hydrothermal vents of this period would have a chemistry that might be propitious for giving rise to a more complex biochemistry that would eventually give rise to life on Earth. How in detail that would happen is the subject of the field of study of understanding the importance of hydrothermal vents for the origin of life on Earth. As the blow up in the images indicates, what the interest in terms of what I'm talking about today is that you form these membranes, tiny vesicles, and within which it's the ideal place for complex chemical reactions to start to occur. So, in other words, a sort of protocell, which would eventually then have to free itself from the environment that we're talking about and become free living in the ocean, etc., and start to have an independent existence, but at the moment would be linked to the geochemistry of these vents. So there's plenty of energy at these vents because there's proton gradients across membranes. This is really an ideal, and there's compositional gradients. So it's really ideal in terms of energetics also for producing a sort of origin of life scenario. And pH gradients also. So you can, in fact, liken it to a membrane fuel cell, which is basically what a little cells are, a sort of fuel cell. And this is another reason why it's seen as being very possible that hydrothermal vents could have had something to do with the origin of life. So in fact, one can perform experiments with chemical garden membranes by putting voltmeters into a system and looking at the voltage across these membranes, and one can play with this system and in the laboratory, I mean, and get some quite nice results, both on the composition of the membrane and on the voltage across the membrane, which is shown here. So you get 0.8 volts across the membrane for a period of over 60 hours in this experiment, which is a very significant result in terms of how much energy there is available in these systems. And you can play by lighting up an LED, by the way. So there are different types of these hydrothermal vents on Earth. The most well-known ones are these low pH and high temperature, so-called black smokers, because they give this black fluid coming out of them. These are probably less involved in the origin of life. They're very high temperature and probably too high for life to have evolved. And then there are these high pH, low temperature white smokers, and these are probably more interesting for the origin of life on Earth. These seem to be much more likely places for the right geochemistry to have taken place. And so these are the places that people are concentrating on, this sort of vent, the high pH, low temperature ones. If you look at these vents in detail, so there's a section on the left showing an overall view, and then a section in the middle in particular is showing the very detailed view of the microstructure. And you see that it's absolutely full of tiny compartments. So this is really it's a type of micro or nanofluidics problem. It brings in another field, as it were. And so the interest here is in understanding how this sorts of tiny compartments could have been driving a more and more complex chemistry on the early Earth towards a sort of self-sustaining proto-cell type environment. So one of the important questions here is that cells are really pumps in a way, that they have to live in their environment and pump things across the membrane. And there are all sorts of ways that cells do this. Modern cells use very sophisticated mechanisms. So here we start, this is just a series of a couple of slides showing the simpler to more complex mechanisms. So simple diffusion is shown on the left, and then you can have channels through the cell wall. These channels can then be active, so that they are actively pumping, as in these examples here. And then in the end, you can have this extremely complex system that goes on in modern cells, where you have a little rotary motor that is pumping the proton gradient across the cell. So one key question for the origin of life is, before you have all of these things going on, how do you manage to have a cell functioning? It has to have communication with its environment, but it also has to be isolated enough from its environment so that it can function as a unit, as a chemical unit. And so you need just enough communication, but not too much. And so a key question is how self-organization can lead to that. So one aspect of this that is now coming towards the physics is, for a start, you need to start to understand in detail the dynamics of osmosis in a porous medium. And well, I've already shown this slide. But the question is, what is the detailed dynamics of this process in terms of the porous medium? One can start to write down the physics of the balance of flow of the solvent and solute molecules across a pore. And when one does that, one arrives at this set of equations, which one can then solve. And here is another version of these same equations. These were originally derived as a set of empirical equations by Kedem and Kachowski some decades ago. And it's interesting and, well, noteworthy that one can actually do this with some rigor and derive these equations and show that this is how the behavior of the solute and the solvent across one pore in a porous membrane should be behaving. Now, this is a sort of origin of life joke, as it were, because there are two, as I said, there are two main theories for the origin of life that are being worked on today. One is the hydrothermal vent theory, and the other is the surface theory, which originally came from Darwin, who called the origin of life, he said it might occur in a warm little pond. And so I have been joking, as it were, that perhaps instead of a warm little pond, it's a warm little pore in one of these porous membranes. So one needs to look at the hydrothermal vent, one needs to look at the structure of the pores, and one needs to consider now the detailed balance of the movement of species across such pores to understand what's really going on in this system. So when you do some physics on this system, make a numerical model of the process, what one finds is that there is a series of different dynamical states for the system. It can be stable, as shown in the upper images, or it can also be oscillatory, you can have oscillatory behavior of the system, and it can also be unstable, and so the protocell would in effect explode. One needs eventually to apply this to actual vents, but to start off with, one can apply it to precipitation reactions in the laboratory. So one can, instead of looking at now hydrothermal vents in the ocean floor, one is making an equivalence with a reaction in the laboratory, and the one shown at the bottom is cobalt plus silicate ions precipitating cobalt silicate. So this is a typical laboratory chemical garden reaction. When one performs this with, on the top left is shown a tablet of cobalt chloride that's reacting, and it's producing a membrane around it as shown in with the arrow. And then one can look in detail at the chemistry and at the composition, and one sees the compositional gradients, for example, which is shown in the lower images. So this interesting chemistry and interesting physics going on in this membrane. Can it be modeled? Well, as I have indicated, yes, it can be modeled. So we need to look at this Kedem-Kachalski type equations, and we need to understand the ingress of certain species into the membrane and the egress of other species, the movement of them across the membrane. So we have to write down a system of equations to describe this. So we can write down equations for the Darcy flow across the membrane, for the concentration of dissolved product, and for the pressure, etc. And then we can perform with this reduced set of equations that you see in above. We can perform a stability analysis, and we see that there are these different regimes depending upon the osmotic pumping and depending upon the formation of solid. So there is a stable regime, an oscillatory but stable regime, unstable, and completely unstable explosive regime as the parameters of the system change. Clearly, the point being here that if life were to get going with one of these self-organized protocells, then it necessarily would have to be in one of the stable states and would have to stay away from the explosive, the unstable state, which would destroy the system. So one can compare the experiments, these are laboratory experiments, we can compare them with the model, and there's reasonable agreement for a simple model system. So one can obtain agreement as to which regime the system is in, that it's in stable, the stable regime, the oscillatory or the unstable regime. It's at least qualitatively a reasonable agreement here, which is considering the complexity of the system is quite gratifying. And so again, experiments and theory are compared here with regard to the lab experiments, and as you see, there's reasonable agreement. We can also see an interesting change in the period of oscillations that we can model with the system of equations that we have, and it produces the curve shown in blue, and that can be compared with experimental changes in the period of oscillations that you see in the also in the graph. And again, there is reasonable agreement. one thing that's notable is that in this system, the flow of ions across a single pore is 10 to the 9 per second, which is very large compared to a modern day cell. So in other words, these will be very leaky membranes in terms of modern cell biology, which is probably to be expected since, well, for various reasons, but if cells today are optimized, then clearly 4.5 billion years ago, they were not optimized. So it's interesting to observe the explosion of the membrane when this thing does explode. Here's a couple of videos showing how this system explodes. These are slow time videos. So what you're seeing is a system slowed down. I forget, at least hundreds of times slowed down. And this is in a very viscous medium. So the explosion, as you see, is producing an oscillation of the membrane. Here's a sequence of images showing the same thing. And so you see the arrows are showing the oscillation, the oscillatory movement of the fluid when the membrane explodes. So the one thing that is noted in this system is a permeability decrease in time. And again, this can be modeled and compared with the laboratory experiments. And similarly to, as I was discussing before, there is a reasonable agreement between the theory and the experiments in these cases. Qualitatively, at least, the same sort of behavior is seen in the model and in the experimental system. So one can model this time-dependent membrane thickness, because this is a system in which this membrane is growing in time as the chemical reaction continues, and so one needs to derive a slightly modified system of equations to take that into account and to show the change in membrane thickness and permeability of the system. As you see here, that can be modeled reasonably effectively also. And another aspect is these systems have a characteristic time. The explosive regime has a characteristic time involved in the explosion that you see. And this can also be modeled with this simple set of equations for the system. And again, the results are reasonably in agreement with what is seen in the laboratory, which is always a good thing in modeling. So another aspect of what is going on in these systems is that we can detect, particularly in what you see on the top left, these images of the real hydrothermal vents, that the membranes are often wavy, and this can also be modeled with this system. And so we can look at the behavior of the precipitate over time and compare with the diffusion across the layers. If you add in the boundary conditions, then you can come up with a system of equations for the precipitate, which you see below. And then one can look at the flow in the gel layer. The gel layer is the layer just above the precipitate, and one can look at the amplitudes of the waves that one sees in the layer and compare it with what the system of equations I just showed predicts. And again, we can get reasonable agreement with between the theory and the experiment on this in this laboratory experiment, which again is quite pleasing. And so, in terms of what I'm talking about today, the interest here is that for the origin of life is that this is a chemically driven type of pump where the walls of a hydrothermal vent are in effect little nano pumps, chemical nano pumps. They have different regimes, stable regimes, oscillatory and explosive regimes. And there is the possibility that the walls of these membranes, because they are wavy, this is of possible importance from the point of view of obtaining more energy from the system, because the flow enhances the transverse mixing across the membrane. And so all of these things are parts of the puzzle to understand how a protocell could have started to form, because this is a completely self-organized physicochemical system. So in other words, you go from a hydrothermal vent on the left to the microstructure of the vent in the middle to what I'm showing on the right, which are these little membranous compartments within which complex chemistry could have started to take place, which have these temperature gradients within them and about them, and we have called them warm little pores. So I'd just like to finish by saying that if you're interested in more information about this, there's a review paper from 2015. So we've called this field Chemobrionics, chemical growth, as it were, and that's the review paper. There are a couple of semi-popular, as it were, accounts, one in Physics Today, one in La Recherche. And thank you to my collaborators in this work. So thank you.
Thank you, Julyan. This was really very, very interesting and fascinating. And the floor is open for questions and remarks.
I have a question.
Please.
So thank you for the talk, very interesting. So one is discussing, of course, also the origin of life, possibly of exoplanets. And there's a very large class of exoplanets around M dwarfs, like the TRAPPIST-1 system, where, in contrast to Earth, the planet may have, from the start, oxygen in the atmosphere, abiotic oxygen, because white dwarfs are initially very hot. So the question is, the processes you were talking about, would they also occur in the presence of oxygen? So if the seawater is, has a lot of oxygen content, so would life be possible, the origin of life be possible if oxygen is there from the beginning?
Well, I'm a physicist, not a chemist, but I think that there's not a particular problem with that from the point of view of this chemistry that I'm discussing. I mean, that's probably shown by the fact that these chemical gardens still are forming on Earth today, when we have plenty of oxygen in the atmosphere. I don't think that that's necessarily as it were, killing the theory. As to whether life could evolve on those planets for other reasons, I'm not sure, but I don't think there's a problem from this point of view.
Okay, yeah, thank you.
Other questions? I would like to ask you a question. I thought that the main puzzle is reproduction. The reproduction of cells, right? That there is this copying mechanism. And I don't see exactly how that is happening in this inorganic system.
Yeah, there are, I mean, I think that the point is that the study of the origin of life is a study that encompasses many different periods within the origin of life. So one has to start off imagining a completely inorganic world, and then eventually one arrives at a world in which there is life. Along the way between A and B, there are many different things to consider. Now, what I have discussed here in this talk is in particular the problem of forming a cell, forming a membrane, and doing chemistry within it. Then another question related, of course, is that chemistry, how it then reproduces itself and propagates to a new cell, etc., etc. Now, it's related in the sense that I didn't go into this, but if you imagine now you have a hydrothermal vent, I didn't even start discussing where the question of the chemistry going on in it. But if you imagine you start to have amino acids that are produced at some point in the vent, they can start to have a complex chemistry within one of these little pores. Then because the vent is an enormous structure, this could, if a particular chemistry which is successful starts to take place in one pore, then it can transmit to the next, to a neighboring pore, etc. And you can start to get a reproduction in that sense. Then you have to start, then you have to basically start up an idea of a Darwinistic competition. So then you can have different versions of this chemistry, and they would be in competition with each other, and the winner would, as it were, take over the vent. And so then the whole vent with all its pores would be with a given type of chemistry. And then these pores, or this chemistry and these pores, would then have to become independent from the vent. So you have to have so everything that I have discussed so far has been a mineral chemistry, but you have to then have a takeover of the mineral world by the organic world. Now, that's a whole other question which is again linked, and I haven't discussed at all, but you have to get lipid membranes formed instead of mineral membranes. And then once you've got the same chemistry and a lipid membrane, then you can start thinking of these vents, these pores budding off from the vent and starting to disperse through the ocean, going through the ocean, finding another vent and reproducing, etc., etc.
Thank you. That's really very interesting.
Yeah, a lot of different questions involved. Yeah.
Sure. If there is I don't see any other question, any hands rising, then thank you indeed. And maybe we can clap our hands, and we can then go over to the next talk. Oh, there is a question. Yvonne Santiago, please.
Yes, just a brief question,
Sure.
because Professor Cartwright mentioned the formation of lipid vesicles. My question is regarding how in such a system in deep sea water with high saline concentration, how can you envision that lipid vesicles formed? Because in the lab we know that is hard, right, to form such vesicles when there's a lot of salt, like in the sea. So yeah, do you have any thoughts on that?
Well, there are. So again, it's the salt concentration is two things. That there's one thing is the ambient salt concentration throughout the whole of the ocean, and the other is the concentrations of salts in local conditions at these vents, at given points in space and time. Now, if I'm now talking about the vent system, then the salt concentrations, there are huge gradients across the vent as salts are used up in precipitation reactions and deposited. And so there are some conditions, there are some parts in which the salt concentrations are reasonably low because of the precipitation reactions taking place. So my answer to that, as a first answer, as it were, is that it would depend on the local conditions within the vent, that you would have to have at some point conditions where this might be suitable for lipid formation, but it's to be checked.
Thank you. Thank you very much indeed. And then it is time to go over to the next talk, which will be given by Giuseppe Gonnella. And the title is Phase Diagram of Active Disks and Dumbbells in 2 Dimensions.
Good morning. Let me share the screen. One moment. Oh, sorry.
Change the.
Yeah, it's a complex procedure. I don't know why I have to do in 2 steps. Otherwise, it's okay?
Yes.
Okay, thank you. So maybe the title is slightly changed. I will speak of the phase diagram behavior of passive and active disks, which means particle with only volume repulsion in 2 dimensions. And let me first thank the organizer for the opportunity of giving this talk, and let me also say that it will be a pleasure to go to Cluj. I don't know if we have already planned to do the conference in the usual way. I hope that it will be so. Maybe you discussed already this point, and it will be a pleasure to visit your university in your town, if possible, in the future. And going to the talk, and I did this work with Letizia Cugliandolo in Paris, Lino Di Gregorio, Antonio Suma here in Bari, in Italy, and Daniel Levis and Ignacio Pagano Barraga in Barcelona. Okay, sorry. Sorry, one moment, what happens? Okay, so let me first tell you some motivation about this research. The main point of this study is to put in relation the phase diagram of active particles, and I will tell you later what they are, with the phase diagram of standard equilibrium hard disk, and with what everything known in this context in research of some years ago. So I will speak about the motivation, which are what just I said, and then I need to tell you something about the passive disk, which means the standard hard disk problem in 2 dimensions, which is something not well known to everyone in statistical physics, even if quite relevant. And then I will tell you something about our result. So let me first introduce what is active matter. Active matter is a very generic word to define, to denote soft matter system or system with many degrees of freedom, where particles can consume some internal energy source to do movement or to make some work on their environment for their life or some other purpose related to their life. Of course, this definition is very broad. It includes a system on many different timescales, going from materials inside the cells, like cytoskeletons. Then you have bacteria or cell colloids, which are the system more related to the model that I'm going to show you. And then, of course, you have other kind of system like men or robots or fish and birds. And the system that I will tell you, that I will speak about are, as I said, more related to colloids or bacteria. They are in this scale of 10 to the -6 meters, where thermal fluctuations are relevant, and they can be considered as out of equilibrium statistical systems, with the difference with respect to equilibrium statistical mechanics, that in this case you put from outside some energy in the system. But in this case, for active matter, this energy flow that you put in the system depends on the local state of the system. This speaking from a generical point of view. To show better what I'm speaking of, I will show you some movie explaining, okay, sorry, what happens. You have on the left a system of Brownian particles, which are standard passive disks that you can simulate by different methods, for example, by molecular dynamics. And you see that in this case, at low density, you have just sort of Brownian motion, and you have some excluded volume interaction between the particles. This is on the left. On the right, I took this picture from an experimental paper by a German group, and these are self-propelled colloids. You have spheres where the two halves of the spheres are coated by different metals, and this produces some chemical reaction in the fluid around each colloid, and this chemical reaction produces a flow that pushes the particles in the direction, for example, of these red arrows plotted in the pictures. So each colloid has a sort of polarity that in the fluid makes it self-propelled in this direction. Of course, if there are many of these, neglecting any sort of attraction, you have not only steric interaction due to the excluded volume, but also you have a sort of effective attraction due to the fact, for example, if you look here to these three colloids, they all push towards the same point. And so, in some sense, they become jammed and they tend to remain sticked together. So, in some sense, you have a sort of effective aggregation interaction. However, I will show you to understand better what happens in a movie. This is these are hard disk with self-propulsion in the sense that I showed you before, and everything is the same as in the other case, with the only difference that here you have self-propulsion. You see that, for example, the particles move much more. This corresponds to the fact that the diffusion coefficient is much larger in this case. But the main point of this talk is what happens if you go to high density. And if you go to high density, I'll show you here another movie at high density. In this case, instead, I found only this movie in my my computer, and this movie is with molecules, not with hard disk, but is the same. And you see that if the density is sufficiently high, aggregates of particles start to form. And this is what is called the mobility-induced phase separation in literature, which is a concept introduced by a group in Edinburgh, Mike Cates and other groups in other places, and much studied around the world. So the point of this talk is if this mobility-induced phase separation is in some way related to the standard melting transition of hard disks. And sorry for this long introduction, but it was a bit necessary. So the point is that if there are equilibrium characteristics of melting transition that are relevant for this mobility-induced phase separation, this is something never considered before in literature. All people focused on the study of these self-propelled particles, and I will show in the next slide the model that we really used, but nobody considered the enormous amount of literature concerning the melting transition and if this melting transition in some way related to the mobility-induced phase transition. So let me just remind you what is known about the melting transition. And if you have a system of hard particle without attraction at very high density, they behave like a solid. But this solid can only have quasi-long range positional order that is characterized by power law behavior for the translational correlation function, and you can have orientational order. Then is not second order, this is a mistake. There is a continuous Kosterlitz-Thouless transition in the standard scenario from solid to exotic system where you only have orientational order. Let me tell you that I'm summarizing a bit of the story that is quite long, and this is a orientational like liquid crystal order, and in this you have dislocation, free dislocation in the exotic, and then you have a further transition of Kosterlitz-Thouless-Berezinski type that where dislocation unbind, and in each dislocation, correspond to a pair of disclination, and this pair of disclination unbind, and you have free disclination in the liquid state. So, and actually, this is the standard scenario that have been a bit changed in the last year by some research of several groups. And the final results is that you go in 2 dimensions from solid, then you have exotic, then you have a region of coexistence between exotic and liquid, and then you have the liquid. So instead of 2 Kosterlitz-Thouless transition due to defects, unbinding, different kind of defects, you have 1 Kosterlitz-Thouless and 1 first order transition. There is a lot of physics here, and on this column you see the plot of the exotic order parameter, which correspond to the density at the 2 limiting point of coexistence. And you go from the exotic on the top to liquid in the last picture. And the first new results in this context is that we have shown that not only you have isolated defect, but you have also percolation of cluster of defects along at the central point of this coexistence region. This percolation is shown looking at the probability of having a size of defect of size n, and here you find the standard laws for percolation, for geometrical percolation for this cluster of defects. But let's go, because the time is going to finish, to active Brownian disk. So we described our system. So this is the almost standard story for passive particle with some more results. So what people have studied, and is continuing to study a lot in active matter, is a system of these propelled colloids where you take some Langevin equation and you have overdamped motion. This is a potential between all particles that represents the repulsion, the volume repulsion. Then you have standard white noise, and then you have this force that depends on this polar vector, and the direction of the polar vector changes in the standard random way. Theta dot is proportional to some other white noise. So in this model, you have two basic parameters to be changed, which are the density and the intensity of the force. And this is the main results of our research. So on the right, you have the mobility-induced phase separation. So this is Peclet proportional to the intensity of the active force. When the active force is very strong, you have phase separation due to activity. All the rest of the phase diagram was not known before. People spoke about jamming transition, or glass state. Actually, there is a very clear relation with what happens with hard disk, and very small, when this Peclet is 0, you have hard disk, and this is a magnification of what happens at small Peclet. So you have solid, the yellow, then you have a very teeny liquid crystal or exotic region, then you have coexistence, and then you have the liquid. At the intermediate value, coexistence disappears. You have solid, liquid crystals, and liquid. And then you have a much more complex situation when you increase Peclet. You see that here, sorry, my finger is not delicate. Okay, so you have, for example, here at this Peclet, just after the critical point, you have, yes, I heard the noise. I know, I'm following the time on my watch, don't worry. And so at Peclet, I don't know, 50, you have coexistence between liquid and gas, actually, and then you have standard mix. So what we added to the phase diagram known before is to complete all the story, and also to see if here there are property of the pressure. Let me tell you that for establishing this phase diagram, we studied the pressure given by a generalization of the virial theorem for Langevin equation, and also studied correlation for the translational and orientational order parameter that I'm not showing. But and many other features were clear, more clear, due to the introduction of this translational order or exotic order. For example, we found that a typical configuration in the MIPS is not, while homogeneous, while you have a big domain, for example, here, all the colored region at the same density, but they have different orientational order. So what we found in these MIPS is that you have another let's say, intermediate land representing the size of the exotic domains. And this feature, for example, can explain the presence of small bubbles observed by other groups in these self-propelled particles that you cannot understand too much without considering the presence of the exotic order parameters. Also here, if you go back to the phase diagram, other groups have studied, for example, the critical properties of this point where coexistence of MIPS ends. And also there, you need to consider the presence of another land, which is the land of the exotic order parameters. And I go to the conclusions. This is the last slide. And we have also studied the case of dumbbells. And in the case of dumbbells, which are two molecules, the same story, but instead of have one sphere, one disk, you have two, which are connected. And in this case, attraction due to repulsion is much more, because these dumbbells tends to be much more jammed one with the other. And the main difference is with the phase diagram of dumbbells is that the coexistence regions without activity of the equilibrium case extends towards the region of high intensity without interruption. While for disk, you have coexistence here and then you have MIPS. In dumbbells, there is a continuous coexistence region going from 0 to any number of Peclet. So what we have done is summarized here. So we have studied the phase diagram of these active Brownian particles, considering also the exotic order parameter and making a connection with everything known for hard disk and putting everything together. And we have studied also the percolation of defects. And okay, I have said already enough. Thank you very much.
Thank you, Giuseppe. We have time for a very short question. Please. I don't see anybody's hand rising. If that is not the case, then thank you again. And we thank the speaker again.
Thank you.
And we go over to the next talk, which will be about elongated particles from diluted two-dimensional systems to dense ones. And it will be delivered by Nikolai Lebovka.
Many thanks to organizer for this nice meeting and your invitation to make this presentation. Now I want to say about this is outline of the talk. First of all, I would like to say a few words about motivations and basic concept definition, then about parking, connectivity, and then conclusion. I want to present our recent review that was issued in this very nice book. And this review is based on many our works performed in recent years in this field. About motivation, I want to say that two-dimensional self-assembly is a very hot topic in modern investigation. I want to say that the shape of the particle dictates the complex behavior, self-assembly, and spontaneous orientational ordering. I want to present a few examples of such self-assembly. For example, this is a symmetric self-assembly. This is a tetratic self-assembly. You see that here we have some stacks of the particles and pneumatic self-assembly. This talk we will analyze the jamming and percolation behavior in one and two-dimensional system of elongated particles. So a few basic concepts and definitions. What is a jamming? The jamming transition refers to the transition from some type of flowing state to another rigid solid-like state. In contrast to the typical crystallized solid, jump systems are generally athermal, that there is no guarantee that this configuration corresponds to the equilibrium state. I want to present here a disco rectangle. They placed on a plane, and the overlapping of particle is forbidden. That's why after some parking, we have the state when we have some holes, but in jump state, we have no additional place for placement of additional particles. Random sequential absorption. The particles are deposited randomly and sequentially on the substrate. and their overlapping is strictly forbidden. We analyzed both continuous and discrete spaces. For example, in continuous space, we have the number density, it's the number of particles per unit area, and then the filling fraction, this is the number density multiplied by the area of one particle. And for example, if we have overlapping particle, the fraction of plane covered by opposite particle is equal to this function where E is a filling fraction. About system with overlapping, for example, we can consider the fully overlapping particle, it's a permeable. Impermeable particle, it's a jamming task. And we can consider also core shell to the particle with a core shell structure. Here I represent to you the particle with a core shell structure. The overlapping of particle is forbidden, but we can allow the overlapping of the shell. That's why in this case we can walk through the particle, and this way is when we have the situation we have the transport through the system. This system is called as a percolating system. Percolation, it's some kind of phase transition when we observed appearance of the giant connected cluster. Sorry. Okay. About oriented system, in real system we can observe the fully disoriented system like this, partially oriented system, fully oriented system in some direction. This state we can be characterized by the order parameter like this, where theta is the angle between long axis and selected direction. This picture is presented for the rather large aspect ratio. Aspect ratio is the ratio between the length of the particle and its thickness. It's equal to 10 in this particular case.
DMR.
Okay. Now let's consider some parking problem. First of all, let's consider the very interesting problem related with the particle of the particle on the line. It's a famous Paris car parking problem. For example, you can imagine this shape represents the car. Car can be parked along the route. The orientation of the car can be different, and the problem is how many cars can be parked on the line. Here we represent the situation when we consider a very long particle, for example, sticks. And you see that when the particle oriented, the preferential orientation is perpendicular to the line. Here the order parameter is a negative. We have such situation. But when we have fully disoriented situation, we have such situation. It's the order parameter is equal to 0. In the case when the particle tends to be oriented along the line, this line, we observed such situation. Its order parameter is equal to 0.5, and in this situation, when the order parameter is equal to 0.9, we have such situation. In all cases, we can observe formation of some stacks. You see, it's a particle oriented parallel, and here stacks, and here we have some holes. For example, this car placed along the line, and we have no possibility to place supplementary particle in this hole. when we have the fully oriented particle along the line, S is equal to 1, we have the famous problem particle along the line. We have analyzed the dependence of the German coverage versus the aspect ratio. Aspect ratio is a ratio of the length of the particle and its width. A different order parameter. You'll see, for example, it's a situation when the order parameter is equal to 0, the disco rectangle line, the order parameter is 0. We have such very interesting behavior. The German coverage goes through the maximum at some aspect ratio. But when we change the order parameter, for example, when we increase the order parameter, we have observed the shift of this maximum. And for example, for high orientation, it's shift here. And when we have order parameter S is equal to 1, for fully
Nikolai, sorry for interrupting you, but can you speak out a little bit, because it's acoustically very difficult to understand what you're saying.
Okay, now
be closer to the microphone a little bit. This is
okay. I'm sorry, it's a problem with my computer. Now it's okay. Now it is okay now. Hello?
Yes, now it's okay.
Okay, so, thank you. So here we have the situation when for fully oriented particle we have no dependence upon the aspect ratio, okay? And with a negative order parameter, we have even more complicated dependencies. And in many cases, we have this gasp-like behavior. This is a famous Rényi-Parkin constant for fully oriented cars. Okay, and for large particles, this decrease can be explained by the excluded volume effects. They dominated here. And this increase can be explained by some effects related with the changes of degree of freedom for elongated particle. We always observed here for particle-oriented particle on the axis, we always observe the gasp. In order to understand it, we have analyzed the for particle-oriented disco rectangle, the correlation function. We have analyzed the density and orientation for correlation function. Here we have orientation for correlation function, and red it's a density orientation function. We always observe a large oscillation, and this oscillation reflects the size of correlated regions of the LCR packing. For small aspect ratio, we have packing like this, and for large aspect ratio, we have packing like this. We have here some regions with holes and some regions with the stacks. And it's very interesting that the location of the first peak in this function, for example, this peak observed a different aspect ratio, and it's here it reflects the contribution of particle with a horizontal orientation, and for this case the contribution of particle in parallel stacks. About the equivalent of this problem for parking of particle on two-dimensional system. In this case, we parked the elongated particle on the plane. You see that there are many different cases as well observed. It's, for example, always for different particle, disk, square, rectangle, etc. and we have also maximum observed, but it's a situation when we observed the situation for partially oriented disk rectangle. Here you see that actual order parameter is not a constant. For example, when we put the order parameter 0.5 in the final system, we have a more higher order parameter. That reflects the situation when we have formation of the domain structure with near-parallel particle inside them. And here I represent for two-dimensional systems the similar dependencies of the jamming coverage versus aspect ratio. You see that in dependence upon the order parameter, we also observed some very interesting behavior. And for the fully oriented particle, we have only increased, but for partially oriented particle, we always observe the gas. Wait, I'm sorry. Okay, I'm sorry. And the similar problem have been analyzed also for elongated particle oriented on the lattice module, for the lattice module. Here, the lattice module, we orient our particle only along the orientation of the lattice. For the square lattice, I represent here as a different packing configuration for the disordered system. You see that for the disordered system, we also observed the formation of the stacks, you see. And for example, for large particle, we have also influence of the order parameter on the packing. Here I represent you the jamming coverage versus the order parameter for different aspect ratio. Chi is the length of the camera. And when we increase the aspect ratio, we can observe with small decreasing of the jamming coverage with the order parameter here increasing. About some words about connectivity percolation. In order to demonstrate the connectivity, it's for example, it's a particle with a core shell structure. We have core and we have shell. The core cannot overlap. And here I represent you the percolation thickness of the shell versus the coverage. You see that we can observe decreasing of the percolation thickness, and in jamming state we have some limiting coverage. Here I represent you percolation thickness of the shell versus coverage for different aspect ratio for disk rectangle. You see that in all cases we have observed some such situation, and in the jamming point we have increasing of the thickness of the cell with the aspect ratio. This maximum at smaller filling ratio can be explained by interplay of geometrical effects, release of orientation, degree of freedoms, and excluded volume effects. The percolation threshold was analyzed also for different overlapping particle, and here we represent the results for overlapping particle, and you see that this percolation coverage versus aspect ratio, we always observe such decrease in function, and in other works also, and the weak dependence of the percolation threshold on particular particle shapes. And finally, our results related with the percolation coverage versus the aspect ratio for non-overlapping cameras. This very interesting behavior, it goes through the medium, you see, and initially when we have only results in the limiting for the limiting value of aspect ratio, we propose that we can observe such behavior. But recently the experimental and theoretical work were performed, and it was proved that percolation cluster in any jump configuration, we always observe the percolation. This is. And conclusions. Conclusions, I would like to say that there are many different real-world systems, including the polymers, biopolymers, nanotubes, etc. And related problem in mixture, vibrated and agitated system are also very interesting. Our recent publication is presented in these works. Thank you very much for your attention.
Thank you, Nikolai. And we have some time for questions. Please raise your hands if you have any. Yeah, I don't see, but please start speaking if because I cannot see.
Okay.
Any question coming up? Okay, so if this is not the case, let me thank you again, and we go over to the last talk of this morning session, which will be given by Stephen Mathey. And the title of this talk is Activating Universality with the Kibble-Zurek Mechanism.
And thanks to the organizers for letting me speak today. Today, I'd like to present some work that I did in collaboration with Sebastian Diel and Björn Ladevik at the University of Cologne, where we looked at universality and the Kibble-Zurek mechanism. So as a motivation, I'd like to point out something interesting about universality and critical points. We know that when a system is tuned to a critical point, we have universal physics emerge and we have critical exponents. What is less known is that there is actually an infinite tower of critical exponents. So for every universality class, there are infinitely many universal critical exponents that are all non-trivial and interesting numbers. They can be real numbers and so on. So the difference is that some of these exponents are negative and they lead to diverging scales as we approach the critical point, while the positive exponents lead to vanishing scales. And so that the negative exponents, the so-called relevant exponents, are easy to observe because they have a dramatic effect, while it's the opposite for the other positive exponents or subleading ones. So what I'd like to try to show you today is that the Kibble-Zurek mechanism is actually sensitive to this whole tower of exponents. And by doing a Kibble-Zurek drive, we can actually bring a subleading exponent to relevance and use it to make a scale diverge. So I will first introduce Kibble-Zurek mechanism. Then I will very briefly tell you about our RG approach that led us to this result. Then I will tell you how these results can be observed. And finally, I will focus on a specific model where we recover the predicted phenomenology. Okay, so the idea with Kibble-Zurek mechanism is that we want to dynamically drive a system across a phase transition. So I represent here a phase diagram with a critical line, and this blue arrow represents a trajectory in the phase diagram with a finite speed. So this tau variable is the distance to the critical line. And what happens is that at the beginning of the drive is really slow, so the physics is adiabatic, and we have coarse graining. We have, coarse graining physics, so we have a correlation length that grows and grows and grows. However, as the correlation length grows, we also have a correlation time that grows. It becomes longer and longer, and the system takes more and more time to respond to perturbations, such that at some point, we necessarily break adiabaticity. And that happens before we reach the critical point, such that there is a finite scale, a finite correlation length in the system. So it means that if we try to dynamically bring a system across a second order phase transition, we automatically imprint a scale onto the system. So that, adiabaticity breaking corresponds, it produces a scale. This can lead to quantitative predictions. For example, here there is a very famous scaling law that I'd like to try to bring you through quickly. So we have our phase diagram again, we have our distance to the critical line that is proportional to time. So I can represent the correlation length as a function of time or distance to the critical point, it doesn't really matter. And what happens is that when tau is negative and large, we have an adiabatic dynamics. So the correlation length is just diverging as it would at equilibrium. And as this happens, the relaxation time also diverges, with Z being the dynamical critical exponent. And what happens is that at some distance to the critical point, adiabaticity breaks. And you can see this by simply seeing that at some point, the distance to the critical point will be equal to the distance traveled within one relaxation time. And by setting these two equal, we can extract a scaling law for tau star as a function of V, and recast as a function of psi star. So this guy here, the correlation length at saturation, we get this famous Kibble-Zurek scaling law. This tells us that the slower we drive the system, the bigger psi star gets to be, the larger the imprinted scale is. This is a universal relation. Depending on U and Z, these are equilibrium critical exponents. So Kibble-Zurek mechanism provides a non-equilibrium probe of equilibrium criticality. And I emphasize again that adiabaticity breaking therefore comes with breaking of scale invariance. We cannot have a full scale invariance if we have dynamics. And for this reason, we went to the RG, because RG is very good with scale invariance and its breaking. So I will not go into the detail of our RG approach. We do some adiabatic renormalization group. I'd just like to point out a few elements, and you can ask for details later on. So when we're interested in a critical system, the RG basically finds fixed points and enables us to compute the critical exponents. So it provides us with a set of exponents together with couplings, and putting everything together, so the GIs are the couplings and lambda i's are the exponents, we can produce scales. And we see immediately that if this lambda I is negative, then setting GI to 0 produces a very large scale. So these GI couplings are basically the distance to the critical point. So what happens is that for the negative exponents, we produce infinite scales if we really go to the critical point, and for the positive exponents, when we go to the critical point, we produce vanishing scales. Now, when we include the drive in the system, for example, here consider a linear ramp where we have the couplings, they have a constant part and some part that is proportional to time. So there's a position and a speed in the phase diagram. And what happens is that now we have twice as many couplings. And if we have twice as many couplings, then we must have twice as many exponents. So I represent here our list of critical exponent at equilibrium. And using our dynamic RG approach, we can actually compute the list of equilibriums, the list of exponents that emerge as a result of the drive. And the really interesting and useful thing here is that the non-equilibrium exponents are actually easily related to the equilibrium ones. For every equilibrium exponent, there is a non-equilibrium exponent that is the exponent minus Z, where Z is dynamical critical exponent. So, and something magic has happened here, because now I had first a set of exponents with one relevant and many subleading exponents, and all of a sudden, one of the subleading exponent has produced a relevant exponent that can produce a large scale. Of course, we need this omega and Z to have the correct difference. So how can this be observed in practice? I zoom in on the left, the most left part of this figure, where we have the most leading exponents that are easiest to observe. So the first line is again the equilibrium set of exponents, and this is the non-equilibrium part. We have now the scales in the boxes. So this is a coupling, the tau is a coupling, and in the box we have a scale, and the same here, we have coupling and scale and coupling and scale. And you see that if I send tau to 0, then I get a diverging correlation length, so that this 1 over y exponent must be nu. It's the divergence of the correlation length as we send T to TC. And simply inserting Y is 1 over nu down there, we recover the usual Kibble-Zurek scaling. So this is good. It tells us that this RG approach produces sensible results. Now, there is a second scale here that emerges as a result of the drive. And this is our new scaling that I'm trying to advertise here. And the way to see, to understand this scale is that now that we have a two-dimensional phase diagram, because there are already two couplings at equilibrium, so that there are two directions in which we can drive the system. And what happens is that if we cross the phase transition head-on perpendicularly, then we see pure Kibble-Zurek scaling. We see this scale here. However, if we can drive the system along the phase boundary, then this scaling takes over. Now, in practice, we see a bit of both. So I return to our phase diagram, and now we consider a drive given by this red line where we cross the phase boundary at an angle. And that means that our drive velocity, this G1, now has two components. It has an amplitude, V, and a direction given by this angle, phi. So what happens if we do the usual Kibble-Zurek drive across this red line? We have a very similar phenomenology. We have first an adiabatic regime where the correlation length is growing, it's blowing up, it's diverging as a power law. And at some point we break adiabaticity, and this imprints a scale on the system. We have this psi star that emerges. However, the difference here is that the psi star depends on the drive amplitude, this V, as a power law with two different regimes. If we drive really slowly, we see the usual Kibble-Zurek scaling, this blue line. However, if we drive faster than some crossover, we see this new scaling regime with the subleading exponents appearing. And the really interesting thing is that this crossover scale depends on the angle at which we cross the phase boundary. I represent this here schematically, where we have the angle horizontally and the crossover scale vertically. You see immediately that if phi is 0, so if we're fully perpendicular, V star diverges and we just see the blue line, we see the usual Kibble-Zurek. However, if the angle becomes close to pi half, if we're crossing the phase transition at a shallow angle, then we can move this V star far away to the left and bring this new scaling regime to an observable status. Okay, so this was very abstract, but I would like to emphasize that up until now, I never really picked a model. So this is an extremely general and exact result. As long as you find a critical point somewhere, in principle, you can do it. Nevertheless, I'd like to finish by picking a specific model and trying to show you that we indeed recover this phenomenology. So we looked at a 1D spin model. This is a XY model. It's a quantum system. We have sigma Z, X, and Y that are Pauli matrices. It's a 1D chain. And this is a particularly nice model for us because it can be diagonalized exactly. So we have a Jordan-Wigner transformation. We can map these spins to a set of fermionic creation operators, which can then be Fourier transformed, and we're left with an independent collection of two-level systems. So this H is now a two-level Hamiltonian that I represent here. And if you are interested in critical physics, it's large scale, so you expand in powers of momenta, and we get this expression down there. And with a bit of experience, you can look at the exponents here, 2 and 1, and recognize Ising universality class. So now that we have a universality class, we can apply the RG approach and look for our phenomenology. Note that there are in principle 3 couplings, J, gamma, and G in there, but gamma can be scaled out. So I represent here a phase diagram with J over gamma, G over gamma. And we're interested in this region where the system goes from being ordered to disordered. And we see different drive protocols where we approach the phase boundary at different angles, phi 1, phi 2. And then I show here in the second figure a semi-analytical / numerical calculation. So we push the calculation analytically as far as we can, and then we switch to numerics. because as soon as you introduce time dependence, it becomes harder. Where we have this psi star, so the saturation scale, as a function of the drive amplitude, and different curves correspond to different angles. So first of all, we see the two different scaling regimes, and the exponents that we measure here are the ones predicted by the RG. And as well, you see that for angles that are very close to pi12, this regime here is large. And as the angle goes away from pi12, then the crossover moves to the right as expected. So before I conclude, I'd like to emphasize that this analysis of this 1D model can give us more information than just what I showed. For example, we can look at different universality classes. So I write again here this two-level system for the Ising universality class expanded in powers of momentum, where we have this 2 and 1 exponent leading to Ising universality class. And starting from there, we defined a minimal model where we picked this as a definition, but changed the exponent. So we consider a model where we have a k to the 4 and a k to the 3 in here. And this is now a new universality class. It leads to a different scaling behavior. It's not super interesting at the level of field theories because it remains non-interacting, but nevertheless, it's a new universality class. And for this new minimal model, we recover the same phenomenology. We recover the RG prediction. We get a crossover that moves in the right direction as we change the angle at which we cross the phase transition, and so on. And another thing that's interesting is that for both models, we also have access to non-universal properties. So for example, I show a figure here of the crossover velocity as a function of the angle. And what the RG can tell us is how this scales as we approach pi12 or 0. But the prefactor of the scaling is completely inaccessible to an RG approach, while when we have a specific model, we can compute this explicitly. Sorry. And this is what we did here, and we get a nice, we get the expected scaling here, and we can compute the full prefactor and so on exactly. So if you want more information, you can look in this paper that should be published very soon, where we analyze this XY model in all detail. So this brings me to my conclusion. So we have generalized the Kibble-Zurek mechanism and showed that it provides access to non-trivial universal subleading exponents. The RG approach that is detailed in this first paper, PhysRev research, sorry. Sorry. So the RG approach is detailed in this PhysRev research, is very general and exact. And we never pick a model and we get a very general result. So in particular, it works, for example, for non-equilibrium phase transitions. Finally, I'd like to emphasize that this Kibble-Zurek scaling that we get from the RG never references defects or domain walls and all the usual Kibble-Zurek phenomenology. So that's one of the reasons why we looked at this Ising model, is that we wanted to check what is the phenomenology here. And what happens is that when you break adiabaticity, you create excitations, and from there you get a scale. So that Kibble-Zurek scaling is actually more general than we thought it was. And with this, I thank you for your attention and welcome your questions.
Thank you for this very clear presentation. And the talk is open for discussion. Zoltan, please.
Thank you. I was just clapping there. This is not raising the hand. But thank you.
So I actually raised my hand. I think I don't know if you can hear me.
Yes, we can.
I'm Andrea Gambassi. So hi. So I have actually a number of questions. So I'll start with the first one. So the model you consider was the 1D quantum XY, so which means the 2D classical.
Yes.
Okay, so then I have another general question. So I mean, the assumption of all your discussion is that as soon as you break adiabaticity, as soon as you break that one, the correlation length freezes. which is actually
Yes.
not true, because anyhow you have coarsening going on, right? So
Yes.
it continues to grow. And I think there was some years ago, there was a detailed study of this issue by Letizia Cugliandolo and others, which they study. I mean, when you say you break adiabaticity, the correlation length then continues growing. So then I was wondering how this can be accommodated in your analysis.
So the way the RG analysis works is that we make an adiabatic expansion, and we can recover. We get reliable results as long as the physics is adiabatic and up until the point of adiabaticity. And as soon as adiabaticity is broken, then the physics becomes non-universal and complicated. And we cannot really say anything. But what we can say is that some scale emerges, and it scales with the Kibble-Zurek or new exponent. You're right that the whole freeze-out part is a whole other question. It's actually really complicated. The freeze-out is the simplest approximation, and I use this here for pedagogical reason, but a lot of things happen in there that we don't resolve.
Because it might well be that because if I remember correctly, it turns out that also after freezing, because of coarsening, you still have some remnant of universality. So that would be interesting, I think, to understand if you can push your analysis also in the region after freezing while coarsening is occurring, because it's anyhow a scaling regime. Okay?
Definitely. So, for example, what happens is there a different coarsening for the Kibble-Zurek scaling or the new scaling? That would be an interesting question, and we just haven't looked at that.
Okay.
We were really focused on the most universal part of the problem right now.
Okay.
Okay. May I have a question?
Sure.
You spoke about irrelevant parameters, but these could be even dangerous. Do you have any idea what is going to happen if this parameter, what you consider it is a dangerous irrelevant variable?
No. So this is a first result, and we went for the most easy case in some sense. Edge cases such as dangerously irrelevant or BKT physics, we haven't looked at right now.
Okay, thank you.
Sorry.
You cannot have everything at the first time. Good. I think that was really a very, very interesting session. Thank you all thanks for the speakers and also for the audience.